Okay, so if you remember last time we talked about filtering, and yeah, so filtering means we want to separate useful from unuseful signals to reduce interference, and one simple example of a linear filter is this filter. What is the purpose of this filter, or what type of filter is this? It's a low-pass filter because the resistance works independent of frequency, but the impedance of the capacitor goes down with frequency, so high-frequency components will be dissipated, go back to ground, and not go to the load. And so if we would write the transfer function of this and say this is some input voltage and this is some output voltage, and if we write down without doing a lengthy derivation the ratio of the output voltage to the input voltage, we can use a voltage divider, and at the end for this filter we end up with something like this, that there is 1 divided by 1 plus j omega divided by omega c. So angular frequency divided by some corner frequency. And the corner frequency in this case, how can we calculate the corner frequency? It's, yeah, so if we would really derive this transfer function, it's 1 over RC. And remember, this also makes sense from the units, because the unit of the resistance is ohm, is volt divided by ampere. The unit of the capacitance is farad, it's ampere second divided by volt. So volt and ampere will cancel, we get 1 over second, and 1 over second is also the unit of this angular frequency or corner frequency. And according to this, I would like to do a small experiment. And so I have prepared, or I've already opened up the rear camera of my laptop. Unfortunately, there is a small reflection on the table from the light of the ceiling. And maybe I zoom out my camera a bit and try to set up all the stuff for this experiment. And so, as usual, I have several boxes with equipment here. And so what we need at first is, of course, some capacitor. And I have a rather large and bulky capacitor here. And I think this should have 0.22 microfarad as capacitance. And I think the 1000 is because it could withstand or handle up to 1000 volts of voltage. And so to build up this simple filter, I have a breadboard, and the first thing that I could do is I could connect this capacitor already to the breadboard. Okay, so this is the capacitor. Then we also need some resistor, some resistance. And so here I have a box that is labeled with 1 kilo ohm. And so I think we could trust that this is also a 1 kilo ohm resistor. So we have some resistor, we have some capacitor, the same as there at the circuit. And I need some wire to be able to connect to the lower pin of the capacitor. And then we need some instrument to measure. And for this, I've brought some scope, some USB powered scope. It's from a company called Pico Technology. So it looks like this. So here we have this scope. And I need some USB cable to connect it to my computer. And then I think once I connect it, it should make some, if it's recognized by the USB port, make some bing bing maybe. Okay, it doesn't, but as you can see, there is some LED that somehow lights up, so it is connected. Maybe the sound is just disabled on my computer. And so then I need two probe cables to be able to measure the input and the output voltage. And it's always a bit tricky with these cables. So there are two cables, and there is one that has a yellow marking at both sides. So this is the cable that I will use for measuring the input voltage with channel A of this scope. And what's also important is that there is some setting here, difficult to see, where you can set this to 1, to a factor of 1 or to 10. And so I will set this to 1, and I hope that, I'm not sure if this is the one. Yeah, this is the one that seems to be a bit broken. So, but that with this, I'm still able to measure the input voltage. Yeah, so this is connected to the input. This is just the ground. I could connect this here, right? And so the second cable, this has red markings. This is what I will use to measure the output voltage. And so this connects to the other side of the resistor. And so I don't need to connect this ground cable because they are already connected here. Yeah, so if I would connect this, it would not make any difference at all. Okay. So channel 1, channel 2, input-output voltage, or channel A, channel B. So then we also need, of course, something to power this filter. And so for this, I have a last cable. And the good thing about this USB-powered oscilloscope is that there's some internal source, which is labeled with AWG. This stands for arbitrary waveform generator. So there's some generator built in there. And with this generator, I can power the circuit, and then the red cable also goes to the input. Okay, so to summarize, channel A measures input voltage, channel B measures output voltage, and this arbitrary waveform generator, let's say it's like a source, like a voltage source that is connected here at this side. Okay, so this is our circuit. So then, before we do any measurements, what I would like to do is open up Octave and plot this transfer function to have some comparison. And for this, we of course also, it would be a good idea to calculate or to use the values of the resistance and the capacitance and to calculate the corner frequency of this filter. So the resistance, if you remember, was 1 kilo ohm. Kilo is 10 to the power of 3. The capacitance is 0.22 microfarad. Micro is 10 to the power of -6. So then we can calculate this corner frequency. Omega C is 1 divided by R divided by C. And we get 4,500 something 1/2. So if we want to calculate the usual frequency from this, what do we need to do? Exactly, take this corner frequency, divide by 2 and by pi, and so we get 700 something hertz. So below 700 hertz, frequencies should pass through. Above 700 hertz, frequencies should be attenuated by with 20 dB per decade. Okay, so now if I set up some frequency range and say, okay, we want to have a log space, for example, from 10 Hertz, let's say, to 10 kilohertz, and maybe with 1,000 points, which should be already way too much. So then we can calculate this transfer function TF. It's 1 divided by 1 plus j times, and now if I write omega divided by omega c, or if I write f divided by fc, right, it does not make a difference. Okay, and so we get then, as you can see here, 1,000 values for our transfer function. And so now we can plot this, and I will also use a double logarithmic scaling. So with respect to the frequency, we can plot the magnitude, the absolute value of this transfer function. And then it looks like this. So if we would label our axis, this is the frequency in Hertz. I don't know why these numbers are still so small in Octave. And this is our transfer function, the amplitude of the transfer function. So for low frequencies, it's just 1. And for high frequencies, we can see here approximately, right here is 100, here somewhere is 700, here's our corner frequency. And if we check, for example, from here to here, we increase the frequency by a decade, and the amplitude also goes down by 1 decade. And 1 decade is 20 dB. Okay, and so now this transfer function is something that we would like to measure from this filter. And so for this, there is a software that is called Frequency Response Analyzer for this PicoScope. And if I open this up, then it does some clicking at the scope. And so if I try to move this window over here, usually you should, there should be also sometimes should happen that this LED is blinking. And so here we can now do some settings. So for channel A, I've used an attenuation of 1. Also for channel B, I've used some attenuation of 1 at the probe. AC coupling is meaningful for what we would like to do here. And then we can set the range and say from 10 Hertz to, this is 100 kilohertz, if we would just go to 10 kilohertz and 50 steps per decade. We should have fairly similar settings. So if I say go, then it's measuring, right? And here you can see the frequency steps. And as mentioned, you can also see this LED blinking here. And it's plotting in blue the gain in dB. And here it's plotting the phase, the gain in dB, and in red the phase in degree. And because we are very close to 0 here, this is mainly the uncertainty of the measurement that we are measuring here. And so now you can see we come close to the break frequency, to the corner frequency of this filter. So this now looks much nicer, and it really nicely fits. If I make this a little smaller, no, I cannot make it smaller, but if I move this down a bit and search for the transfer function that we have calculated from this filter, it looks fairly similar. So this is not yet scaled in dB. If we would like to, for better comparison, if we would like to scale it in dB, what would we do with the transfer function here? Take 20 times the decadic logarithm of this. Oops. And so if I replot, I think there's some closing parenthesis missing. So then it looks like this. now it's not looking meaningful anymore because we have converted into decibel, but still we use a logarithmic scaling for the y-axis. So we need to go back to some semilog x plot where just the frequency axis is logarithmically scaled, and then it looks like this. And so then you can see here we start with 0, we end with something like between 20 and 25. Here we start with 0, we end with something between 20 and 20, minus 20 and minus 25. So this looks nice. How could I do a comparison for the red curve in Octave? How can I calculate the argument of our transfer function, this phase angle, this phase shift? Yeah, the square root and real part squared, imaginary part squared gives us the magnitude. This is what we already have. How do we get the phase angle? We could use some inverse tangent function, arcus tangens, or we could just say angle. Angle of some complex thing gives us the angle. And this will be in radians. We want to have it in degrees, so we multiply with 180 divided by p. And so I should have plotted this into a second plot. So I will plot the transfer function magnitude once again, open up a second figure, and then inside the second figure plot the angle. And so this is the magnitude, this is what here is the blue curve, this is the angle, this is what in the lower plot is the red curve. And we see a very nice agreement from my point of view between the theoretical transfer function, the calculated transfer function, and the real measured transfer function of this filter.